We've already seen how to do the dot or scalar product and the vector product or the cross product. We can do a triple product by combining three vectors together with a combination of both the dot and the vector or scalar or the vector product. It's called the scalar triple product. The word scalar implies that the answer to all this is a scalar, and we've got three vectors. There's only one way we can actually calculate this, even though you think maybe we could do the A dot B first. If you did the A dot B first, the dot product, as you know, when you do the scalar product, the answer is a scalar. So you'd have a scalar with a cross product of a vector, which is undefined. So you can't do the A dot B first. The only way to do this is B cross C. B cross C being a vector product, the answer is a vector. And then you've got a vector dotted with vector A, and that will be manageable, and we'll be able to calculate that, and the final answer will be a scalar. So the way to do it is to do the cross product first and then do the dot product last. So just to remind ourselves, we might put brackets around that, even though they are superfluous. So let's just put these into a diagram, and we've got vector B, vector C. You can imagine those two vectors being in the page and vector A coming out of the page. And we'll go ahead now and calculate these step by step. So we've got this is equal to A dotted with, now by definition, B cross C is the absolute value of B, absolute value of C, sine of the angle between the two, the sine of the angle is alpha, a unit vector perpendicular to both B and C, which is N, and this is B cross C. This is a vector because you've got a scalar, 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 and this is a vector. So we can multiply a scalar times a vector, not a problem, just normal multiplication. Okay, so we've evaluated B cross C and got that. Now, previously we've shown that the cross product can be geometrically interpreted as an area. B cross C is the area of the parallelogram formed by vector B and vector C. So let's just draw out a parallelogram. C will draw this one parallel to C, this one here will draw parallel to B. So this is the absolute value of B cross C. B cross C is actually a vector, as you know, and it would be perpendicular to both B and C. So it would be going up that dotted line, would be B cross C. Okay, so our next step is to do the dot product now, and by definition it is the absolute value of the vector on the left, the absolute value of the vector on the right. Now this is a vector, so it'll be B, we'll do some smaller absolutes, vector C, sine alpha N. It is the absolute value of the vector on the left, absolute value of the vector on the right, and it is cos of the angle between. Now here's B cross C, the angle between B cross C and A is theta. Okay, when we evaluate this, we can do the A, because this is a scalar, this is a scalar now, and this is a scalar. So A cos theta, what's A cos theta? The absolute value of A is just the length of that. Cos theta would be the projection of this length on this perpendicular here. So if you like, you could draw a little right angle triangle there. A cos theta would be the length of that line there. Okay, now geometrically then, we've got this here being the area of that parallelogram, and as you know, area of base times height gives volume. So if I drew another line parallel to A, and all those would be parallel to A, connect them all up, we have a shape there that is called a parallelepiped, and it's just the word parallel, an E, and then a piped. And a parallelepiped is a solid shape that has a base of a parallelogram, sides that are parallelogram. So base and top are parallelogram, and all the sides are parallelograms as well. They're not vertical sides. So A cos theta is the height, area of base. So this would be the area, oh sorry, it's not the area, that's the area of the base times height is volume. So the scalar triple product can be interpreted as the volume of the parallelepiped formed by the three vectors A, B, and C. So it's a volume. Okay, now what happens if the scalar triple product is equal to 0? If that's the case, that means this parallelepiped has no volume. So how could we draw A, B and C so that we don't get a parallelepiped? There is only one way that can be done, is if A lies in the same plane as B and C. So A would have to somehow or other lie in the same plane. If you like, A, B and C all lie in the screen that I'm writing on. So A, B and C are all in the one plane. Now when things are in the same plane, we say they are coplanar. And that is a test sometimes. If you're trying to find whether three vectors are coplanar, you find the scalar triple product, and if you get an answer of 0, then they lie in the same plane. All right, so just going back over again, we've got the scalar triple product. It is A dot B cross C. The only way to calculate is to do B cross C first, and then we can do the scalar product with it. Now, B cross C is the area of a parallelogram formed by B and C. Incidentally, a half AB cross C is the area of a triangle. If you drew a diagonal this way, it would be half B cross C would be the area of that triangle there. But B cross C is simply the area, or the absolute value of that would be the area of that parallelogram, and then we do the dot product A, we get the volume of the parallelepiped.